My name is Jean-Rémy Lherbier. I'm a civil engineer for Artilia Group and in the fields of dams and hydropower. I will talk a bit about the assessment of flow acceleration response spectra and its application to the case study of Marèche Dam with the calculations that we carried out with Frédéric Andrian. And keeping in mind question, is it really relevant for low seismicity structures? So a few informations regarding Marèche Dam. It's a 82 meter high dam, arch dam, located. You can see the location in France on the map on the right corner. It was built in the 30s for hydropower, and it's currently operated by the SHEM. We will talk in this presentation about the spillway gantry that you can see on the photography. Based on a previous study that was carried out in '99, the acceleration was about 0.6 G at the base of the gantry, and which the model leads to an amplification of the PGA by a factor of 5.7. Based on those results, the ECE load case was designing, and a strengthening of the spillway gantry was required. But looking at the seismicity map of the France, the Marèche Dam is located on the weakest area of seismicity. So question was raised regarding the assumption considered for the calculation. And prior to strengthening, Artilia carried out an advanced numerical modeling in order to reassess the amplification at this location with other assumptions. Just a quick close-up view of the spillway and the spillway gantry. As you can see, the spillway gantry is not located directly on the rock mass, so there can be a bit of amplification through the spillway. So let's talk about the seismic input. Prior to the calculation, seismic hazard assessment was carried out. In order to avoid questions from Pierre-Yves, this was carried out by a deterministic approach that was not of our choices. So that was an input for the calculation. The PGA is very low, is about 0.10 G for both horizontal and vertical components. And for information, this is higher that was requested as per the previous working group on dams and earthquakes, which was a national one commissioned by the government. We carried out time history calculation. So we generated 3 sets of synthetic accelegrams for both horizontal and vertical components. You can see an example on the left corner of one accelerogram, the set one number 1, and on the right corner you can see the spectrum of those accelerogram fitting the site spectrum. Few information regarding the foundation. The Marèche Dam is located on a granitic foundation. The mechanical properties of the entire numerical model was based on the previous calculation, which was calibrated on the monitoring data. And in order to assess the dynamic properties, the ratio illustrated were used, which means the dynamic rock properties were multiplied by 1.5 regarding to the static one, and for the concrete it's multiplied by 1.25. There is 3 zones of different geotechnical parameters in the model that influence the seismic response. As you can see on the right bank, the blue part is not that stiff, with a modulus of 7.5, whereas on the central part there is a dynamic modulus of almost 50 gigapascal. The numerical model was carried out by means of Flax 3D code, which is developed by Itasca. You can see the model on the right part of the slide. The the mass of the foundation is considered through the calculation. So the wave propagation is solved all along the foundation, and the mesh was the model was selected in order to solve frequencies up to 20 Hertz. Due to the difference of the stiffness, you can see that there is the difference in the meshing according to the zones of the foundation. The model is composed of almost 175,000 hexadominant elements with a mathematical formulation of a mixed discretization scheme in order to avoid locking, shear and volumetric locking of the zones. Every element of the model is modeled by means of the same elements, which for the three parts, the dams, the reservoir, which is modeled, and the foundation. The same elements are used for the three of them. We also consider the four advanced dynamic interaction features that were also explained in further studies in the previous study, such as the Tagokura Dam. We considered under the input applied at the base of the model was calibrated in order to obtain at the outcrop illustrated on the red at the outcrop, which is in the free field, to obtain the seed spectrum. Radiative boundary conditions were considered in order to model a nearly semi-infinite foundation continuum, and which has such features as a significant influence on the model seismic response with a decrease ratio up to 2 or 3. The reservoir was modeled as by means of compressible solid zones, which is quite different from the Westergaard hypothesis. Doing so, the reservoir may either behave as a Westergaard, which is only one particular solution of the wave propagation, or may also act as a generate additional damping, depending on the ratio of the eigenfrequencies of the dam and that of the reservoir. It depends on the model and the geometric component. And both horizontal and vertical seismic components were considered through the calculations. These features was required for the best fitting calibration of Tagokura Dam previous study. The entire calculation was elastic, which means that there is no no energy dissipation through the materials, nor at the interface between, for example, the joints of the dam or the joints between the interface between the dam and the foundation. This is a conservative approach. Consequently, it will maximize the amplification at the gantry crane, at the gantry of the spillway, sorry. And the Rayleigh viscous damping was considered only for the concrete, and it was based on the range of the eigenfrequencies of the model based on the previous study. The magnitude of the Rayleigh viscous damping is about 4 to 5% in the area of interest. In order to compare our result and to make a check with the 99th study, we monitored the result at key location of interest that you can see in red, and on the figure you can see the previous numerical model superimposed with the one that we carried out. In this particular analysis, we will focus on the points that you can see on the right bank, the point number 273 and 71, which are where the gantry of the spillway is located. Talking about amplification, we assess the amplification through the model by means of the following methodology, which means we consider the input that we applied at the bottom of the acceleration applied at the bottom of the model. We attest the corresponding spectrum, and we also monitored the acceleration at the key locations as explained on the previous slide, and we assess the corresponding spectrum. And what we call amplification is the high frequency result of high frequency ratio both spectra. Sorry. Regarding the previous calculation, we had several issues regarding the horizontal seismic component direction. In the previous modeling, both horizontal bank-to-bank and upstream to downstream components were simultaneously applied, corresponding to the same seismic solicitation. This leads to an overestimation of the horizontal seismic component, which is in this case multiplied by a ratio of by a square root of 2, and which is also questionable because for example, in this particular load case, even if the signal are oscillating from the right side to the right bank to the left bank and upstream to downstream, in this particular case, it leads to a very stiff behavior of the dam on the left bank due to the rock support, which increases its stiffness, and the more unfavorable response on the right bank, which is the key of interest, which is the key location of interest. So we did carry out this calculation as per the previous assumptions, but we also carried out 2 additional load cases, considering either the horizontal component applied only radially, which is the most unfavorable, which will lead to the most amplification at the location of interest. And the other one was to consider an orthoradial horizontal input, which is in this case very favorable regarding to the amplification. And then we provide, our job was to provide those information, those amplification, structural calculation were not on our part. So the structural calculator can do the numeric combination as per as well. Just a few results regarding the acceleration profile on the central cantilever. You can see the result from our model on the blue line, and the result from the previous study and the dashed red line, which leads to a significant reduce of the crest acceleration, which was from about 19 on the previous study meter per square second, and almost 6 in our result. So it is almost divided. It's more than divided by 3. If we apply both the horizontal component as on the previous study, we observe that the key location of interest a reduce of the seismic acceleration by a ratio of almost 60% everywhere, except on we don't have the result on both banks. That's why it's not shown. Except on the location 71. This can be easily explained by the fact that this location is very close to the top of the sorry, is very close to the rock foundation, so the amplification is almost the same as in our model. So the 13% differences is quite low. And now, if we carried out the calculation as per our methodology, in blue it's the result for radial solicitation, and in red as per orthoradial, which minimize the amplification. As we can see, we have a radius of the a significant decrease of the amplification at the key location of the gantry of the spillway. Previously, we had 5.7 on the 99 study, and now we have a maximum of 2.2 on the left part of the gantry. And the results are almost similar on the right extremity. So in order to conclude for the study, the strengthening of the gantry crane was avoided, and which was it was avoided due to the reduction of the amplification. On previous study, we have seen that with advanced features, an acceleration decrease with a ratio of about 2 to 3 was expected, and it is confirmed with this study also. There is a question regarding the orientation of the horizontal component for an arch dam, because in our case, the orientation of the horizontal component was quite obvious, because we were only interested of the acceleration and amplification at one location. But if we want to assess the overall seismic behavior of the arch dam, the question can be raised, because if you can see on the screen the two comparisons, for example, of a NUMAC comparison, a combination considering one component in red and the other in yellow, the behavior of the dam will not be the same considering what is expected, what is shown on the left side and what is shown on the right side. It depends on the location of interest of the dam. With classical calculation methods, the seismic response is often overestimated, and there is a risk of unnecessary strengthening. As we have seen with advanced calculation methods and features, there is a low seismic response. But the question is this really necessary to carry out such calculation, which can be costful, in order to assess the seismicity of such structure, for example, with a PGA of about 0.1 G. In the French, since those calculations, there was a decree in France, and the seismic acceleration for low seismic for dams in low seismicity area are not defined anymore. So the problem is almost solved, but the question is still raised for international structure and calculations. And one calculation that is usually required is, for example, not for dams but for powerhouses. In such case, it is often requested by the electromechanical supplier to assess the amplification through the powerhouse. And as we can see on this figure, applying a 0.16 G on the base of the model leads to almost 1 G at the top of the model. And this can lead to very significant issues regarding electromechanical equipment. And the problem is not maybe an issue of the amplifications through the model, but of the input that is considered. For example, in this case, this is an underground powerhouse, and is it really necessary to consider a 0.6 G at the base of the powerhouse, or maybe we can consider it at the outcrop of the rock foundation? So that was all for my presentation, and I'm available for any questions.